Hey guys, this is Dr. Asmat Fatima, and I have done my post-graduation in the field of conservative dentistry and endodontics from Aligarh Muslim University. So now today I have made this video all about the endodontic instruments, and this video is just about the basics of the endodontic instruments, that what kind of alloys are used for making these instruments. Later on, I'll try to post another video in which there'll be details of the endodontic motions, all the instruments, all about the K files, H files, and the recent advancements in the field of rotary endodontics. So let us begin our video. So any time when you are planning to do a root canal treatment, one thing that you should keep in mind is that always try to maintain the original shape of the canal. Like suppose if the canal is curved, always try to shape it in a way that it remains curved only till the end of your preparation. Okay, do not try to violate the rules or the objectives of root canal preparation. So for root canal treatment, you will be basically requiring your endodontic instruments as well as the irrigating solutions. So endodontic instruments, they are of two types. The first one is the handheld instruments and the other one is the rotary instrument. Okay, so earlier when the instruments, most of the instruments, they were made of stainless steel, but now there have been a shift in the alloy, and that is we have shifted to NiTi instruments more. So let us discuss about the stainless steel instruments first. So one thing which is common in the stainless steel instrument is that it has got a specific property which is known as stiffness. As the instrument size increases, you must have seen number 6K file, number 8K files. They are not that stiff as compared to number 40, number 35. So as the size increases from number 6 to further, when you will move on, you will see that one thing which is getting common is stiffness is getting increased as the sizes increases. So what happens is when we are using these stiffer K files in a curved canal, so these files, they always have the tendency to return back to the original shape, that is to straighten themselves within the canal. Suppose you are preparing a curved root canal. Okay, you have inserted your file, but that file, it is stiff and it has the tendency to straighten, so there will be chances of procedural errors such as ledges, canal blockages, or it can lead to perforations, transportation, zipping. All these procedural errors can happen with the use of stainless steel files which are stiff. So these stiffer files, they will cut more on the convex or the outer side of the canal rather than on the inner side. So therefore, to recover from these stiffness properties and to get something better, Walia et al. Introduced the concepts of NiTi in endodontics. So nickel titanium alloy nowadays is used for majority of the instruments which is used in root canal treatment. So this nickel titanium alloy, it is also known as nitinol, whereas Ni stands for nickel, Ti stands for titanium, and NOL is for Naval Ordnance Laboratory, and it contains 55% of nickel and 45% of titanium. So there are several advantages of NiTi files over the conventional stainless steel files. That is, these files, the NiTi ones, they have got increased flexibility, they have got torsional resistance, cyclic fatigue resistance. Now these two terms, they're very important and we'll be discussing it further in this video, so stay tuned. And then these NiTi files, they have got shorter treatment time, they have got super elasticity, shape memory. These are all the features of NiTi files. So they have got corrosion resistance, and there are very few chances of procedural errors such as zipping and ledges. So, but despite of their superior mechanical properties, they also pose some risk of fracture. That is, it is common, the risk of fracture, it is common both for stainless steel as well as the NiTi files. So a lot of different processing procedures have been introduced in these NiTi alloys to make it better, to make it like more fatigue resistant, Okay, so these treatments, they include thermal treatment, mechanical, electropolishing, and electric discharge machining. So all these procedures, they are incorporated in the nitrile alloys so that they can have superior mechanical properties. So the main purpose of these treatment is to incorporate more of a martensitic phase into the files. Now what is martensite? You need to know that basically the nitrile alloys, they exist in two different forms. The first is the austenitic phase, that is at the body temperature. Most of the files, they are in the austenitic phase, and then there is another phase which is known as martensitic phase. Okay, and in between these phases there is one more phase which is known as rhombohedral phase or R phase. So we'll be discussing it later. So a lot of manufacturing companies, what they are trying to do is they are trying to incorporate more of a martensitic phase into the files so that they can gain the maximum advantage of flexibility. Okay, so you just remember that more of the martensite, more the flexibility. Okay, so now these heat treated instruments, like I've already mentioned that thermal treatments are being made in the files. So these heat treated instruments, they also possess improved cyclic fatigue resistance as compared to the conventional nitrile alloys. Now, okay, let us see nitrile alloys. I've told you that they exist in two phases. One is the austenitic phase and the other is the martensitic phase. So all the conventional nitrile files or the instruments, they were mainly in the austenitic phase, and now recently the heat treated or the controlled memory wire or the pro taper gold, vortex blue, all these files, they are more in the martensitic phase. So the instruments, this thing is very important. Keep in mind that the instruments which are based on the austenitic alloys, they possess super elasticity. Okay, so austenitic alloys will be there, so there will be more of a super elastic property, and martensitic alloys, when it will be there, it will have more of the shape memory effect. Okay, so these things you should remember, that more of the austenitic phase, more super elasticity, more of the martensitic phase, more shape memory effect. Now see, suppose this is the austenitic phase, so when you will cool it down, it will get converted to martensitic phase. Okay, but in between the entire conversion from austenite to martensite, there's one more phase in the intermediate phase which is known as rhombohedral phase or R phase. And again, this martensite, it will get, when you will apply stress, it will get deformed. So this is deformed martensite, and when you will heat this phase, again it will revert back to the austenitic phase. So this is the basic mechanism of the nitrile alloy. So these alloys, they exist in basically three phases. So this R phase transformation, this R phase, it has got the properties of both the shape memory as well as the superelasticity. Okay, austenitic, you have seen that it has got superelasticity, martensitic has got more of the shape memory effect, and this R phase, it contains both the properties. So you'll see the austenitic phase and there is a stress induced martensite. So how can we convert this austenite to martensite? The one thing is that if you apply stress, that is if you load the austenite, okay, stress if you'll give, then it will get converted to martensite. And one more thing, when you'll cool it down, it will get converted to martensite. Similarly, if you want to convert it back into the austenitic phase, you need to heat it down. So what is like earlier I'm saying this shape memory effect, super elasticity. Now we need to know what is shape memory and what is super elasticity. Okay, so shape memory, it is the effect of restoring the original shape of the plastically deformed material by heating it. Okay, already we have seen that martensitic phase has got more of the shape memory effect. So when you will heat it, back, it will get converted to austenite. Okay, so this involves the transformation of the deformed martensite to austenite, and is mainly because of the heating. Now this martensitic phase, it is more flexible than austenitic phase, but still the martensite favors reducing the risk of file fracture under high stress. Why? Because suppose you have inserted one instrument in a curved canal, it is undergoing high stresses. What will happen, that this martensite, it will not break down, it will get deformed. Okay, so so more of the martensitic phase, the lesser the chances of file fracture. Okay, so now to incorporate martensite into the commercial NITI instruments, a lot of technologies, a lot of instruments are available in the market. So the instruments such as M-wire technology instruments and the CM wire instruments. So we will be seeing that the M-wire, it is patented by Dentsply Tulsa, and the files which have the M-wire technology is Profile Greater Taper X, Profile Vortex, and Profile Vortex Blue. Okay, so all these files, they contains more of the martensite. Then the CM files, that is CM stands for controlled memory. So the CM files such as high flex CM files are there, manufactured by Colteen. Then Typhoon Infinite Flex NITI files are there. So they are also more in the martensitic state. And what is one basic property of these CM wire is that they can return back to their original shape when you will autoclave them. Like these files, when you have when you are placing it in the curved canal, they will take the shape of the canal, and when you will pull it back, it will have the same shape of the canal. That is controlled memory. Okay, so now if you want to use it again, you can autoclave it, provide heat, and it will revert back to its original shape. But these files, the manufacturers, they mostly recommend that these files are single-use files. You should use it only in one patient and then you should discard it. Now the manufacturers of these files, they also claim that these instruments, they are up to 300% more fatigue resistant, and they have no rebound, and they can regain their shape after sterilization. Now we have discussed about shape memory. Now it is super elasticity. So super elasticity means, the word itself, it's giving you the meaning. Okay, super elasticity, that is a lot of flexibility is there. So why the austenite? We have seen that austenitic phase files, they have more of the super elasticity property. Why? Because when they are stressed, they can bear the load and they get converted to stressed martensite. Okay, so in this phase, until this is austenite, unstressed austenite is converted to stressed austenite, it can bear the property of super elasticity or flexibility. Okay, so to utilize the super elasticity of NITI alloys, it should be in the austenitic state, which is the high temperature parent phase of the NITI alloy. And most of the conventional NITI instruments such as the Profile GT, M2, Lightspeed, Quantec, all these instruments, they were mostly in the austenitic state. So these instruments, they can be inserted easily into the root canal because of their high elasticity and flexibility. And when external stress is applied within the canal, then what will happen is that they will get converted into stress induced martensitic phase, and they will give rise to more of the elastic material. Now I've told you that we'll be discussing about the cyclic fatigue and torsional fatigue. So basically the file fractures because of these two phenomena only. One is the cyclic fatigue and the other one is the torsional fatigue. Now the cyclic fatigue is like, fatigue means like, in general term, if you are using this word fatigue, it means laziness or tired. Okay, so when you are using the file repeatedly, okay, in a canal, so what will happen? Suppose you have inserted one file, rotary file, it is moving inside the canal and it is going repeated to and fro motions. Okay, now what will happen is that because of the continuous rotation, there will be a generation of tension and compression forces on that file, and eventually at one point what will happen is that that file will break. So that limit will be the cyclic fatigue limit. Okay, and torsional fatigue is, suppose you have inserted your file and the tip of the file, it binds within the canal while the shank or the upper part of the file is continuously moving. So at one point there will be enough torque to break it. Okay, so that is torsional fatigue. So these two are the major mechanisms of any file fracture. Okay, now one thing, one drawback of NITI instruments is that they do not give any warning sign as opposed to stainless steel instruments. So we cannot perceive when your file is going to fracture. Okay, so it's better that you should not use a single file multiple times. Okay, limit your usage of the files. Okay, then only you can prevent it from getting fractured. Now, torsional fatigue resistance is basically how much a file can twist before fracturing. And this property is very important, and we need to have this property when we are using our instruments in a narrow and constricted canal, because in that canal there'll be a lot of torsional loading. So manufacturers, they are constantly trying to develop several changes in the night-eye rotary instrument so that they can improve the properties of these instruments. Okay, and one of the changes incorporated was heat treatment of these alloys, like the thermal treatment I've discussed, the M wire and CM wire. So by incorporating all these treatments, we can get superior mechanical properties of the night eyes. Now, thermal treatments are there. So one treatment is like there are several kinds of heat treated night alloys. The first one is the M wire, the other one is the R phase, and the next one is the CM wire. So these are the technologies. Like, you must have heard that this file is using M wire technology. Suppose high flex CM is using controlled memory technology. So okay, these technologies, these things, they are patented by several companies. Like Colteen ka CM wire is there, okay, Dentsply ka M wire is there. So you'll get to know about all these files. So first, if let us discuss about the M wire. So this technology, it was introduced in 2007, and it is basically a thermally processed night alloy that is stable at body temperature. Now, M wire, it contains austenitic phase and a small amount of martensitic and R phase. So majority of the phase, the major phase is the austenitic phase, while few or small amounts of martensite and R phase is also incorporated in this technology. So more of the austenitic phase is there. So remember what we have told earlier, that more of the austenite, more of the superelasticity. So the presence of martensite, it will improve the fatigue resistance of the file. Okay, now there are several examples of the M wire files available in the market, which is known as Profile GT series, Profile Vortex files, ProTaper Next, Reciproc, and Wave 1. So all these files, they are using the M wire technology. They have more of the austenitic phase and they have more of the superelastic properties. Now we'll see that this is a conventional stress strain diagram. So you can see in this diagram that less stress is required to induce martensitic transformation in M wire than in conventional night eye. Suppose the file is in the austenitic phase, it is under stress, okay, it is under constant loading. So ultimately it will convert to the martensitic phase. So if you are using the M wire files, then they will require less stress and they will be getting converted to martensite. Okay, so these M wire, they possess a lower elastic modulus as compared to the conventional night eye, and these M wire files, they also have greater flexibility than the conventional night eye wire. Next phase is the R phase. So R phase is also known as pre-martensitic phase. That is, before the actual conversion of austenite to martensite takes place, there is an intermediate phase which is known as R phase. Okay, so these instruments, they also have increased cyclic fatigue resistance, they have a greater flexibility, and these treatment, the files which are mainly in the R phase are twisted file and K3XF. Next one is the CM wire. It was introduced in 2010 and they have a lower nickel content as compared to other night eye files. Now, to incorporate extreme flexibility, these files, they should undergo a special thermomechanical treatment which will improve the shape memory effect of these files. Okay, so these files, they do not have the rebound effect. You have seen the ones from the Colteen high flex CM. What will happen with these files is, when you will introduce it into the into the canal, it will take the shape of the canal and it will not rebound back. Okay, it will only be reverted back when you will apply heat, that is when you will autoclave it. Okay, so these files, they are mostly in the martensitic phase. Okay, the CM alloys, they are mostly in the martensitic phase, and the manufacturers, they claim that they are having 300 to 800% more fatigue resistance. So, but one major drawback of these files is that they have the increased tendency of permanent plastic deformation during use. So they are just for single use only. Okay. So now we have discussed about the alloys, the phases in which the NITI files exist. Now later on I'll make another video. I'll try to make another one in which we'll be discussing about all the types of endodontic instruments, such as the H file, K file, the rotary files, their usage, how to use them. Okay, so see you in the next video, and please, if you like the video, please do like, share and subscribe. Thank you.